So last time we emphasized those adiabatic relationships so that we're not like GRU. We get into the middle of this thing and we mess those up and get the volumes wrong and so on. And then we'll see today too that we can model any thermodynamic cycle by breaking it up into tiny little Carnot cycles. So we can agree with Buzz there. So this is the reversible Carnot cycle. Notice we've done other kinds of cycles that had like isobars in them or isotors, constant volume legs. Notice how this one, all four legs are curved. All four legs are reversible. And these are the most efficient ways to do expansion and compression. The next lecture, we will apply this to real engines, and we'll look at the automobile or auto cycle and then the diesel cycle and the Brayton cycle too for jet engines. So we'll apply this to those others, but in general, today is the sort of classic lecture on the Carnot cycle. This is the most efficient cycle that we have. So let's look at the four legs that we have and the equations associated with them. Okay, so this first one, this first leg, A to B, is isothermal expansion. Since it's isothermal, let's go through and look at all of the things that fall out from that. So delta T equals 0. Therefore, there's no change to the internal energy, because the internal energy is the CV times delta T, and if delta T is 0, then there's no change in internal energy. So the work and the heat are same magnitude, opposite sign. So when you find one, you flip the sign, you've got the other. Okay, and so we know that the governing equation for isothermal expansion is this reversible isothermal expansion work equation. Don't forget the minus sign. Okay, and then you've got VB, here's the final, and then A is initial. So this is greater than 1, so we would have the natural log be positive, so work would be negative. That's the system doing work on the surroundings. Now, think about what we're doing. This is a clockwise cycle. And the working gas is pushing on the piston. So if it's pushing on the piston, it's doing work, right? That's a simple concept of work. You're pushing on a piston that's turning a crank and driving your vehicle or whatever it is forward. It's mechanical motion. So it has to be doing work when it's expanding. And that means that it's negative. It's a negative number. So when your working gas is doing work, it's negative because it's losing joules of energy by doing that work. So if you get VA and VB flipped, that will cancel the minus sign. You'll have a positive work, and you're not going to have positive work on expansion. Expansion, you have negative work. It's doing work on the surroundings. So then we get to the adiabatic leg. Adiabatic, that word right there means Q is equal to 0, no heat flow. And so then the work done is the internal energy. That's that first law, right? So we can do that. Delta U is equal to Q plus W. So if Q is 0, then the work is equal to delta U, which is just the number of moles times the heat capacity at constant volume times the change in temperature. And here, this is the hot isotherm, TH. You see the H, TH, and this is the cold isotherm, TC. So the final temperature is TC, and so we're going from hot to cold, and so it's T final minus T initial. So T cold minus T hot. So cold is lower than hot, so we're going to get a negative number out of this, and it's an expansion, so that's good. Our work will be negative. Okay. So I'll just put these little things, less than 0 here, less than 0 there, right? So both of those are negative. Then we reset the system. This is the maximum volume. VC is Vmax. And after we're at Vmax, we've got to squeeze the gas or the piston and reset the system all the way back up to point A. So we're going to do work on that gas and compress it. But it's easier to compress because we're at a colder temperature. So that would make sense, right? If you got a hot gas in a box, it's going to put more pressure on the walls. If you cool it down, then you can compress it at a lower temperature, and It's going to require less work to compress that gas. Now it's isothermal, okay? So isothermal means delta T is 0, delta U is 0, Q and W are equal magnitude, opposite sign. This fraction is less than 1. Therefore, this natural log is going to be negative. And so then that negative sign cancels this negative sign. And so then this whole thing is going to be greater than 0 or positive. Question. And then the same kind of thing, adiabatic compression, MQ is 0. Therefore, the work is equal to the energy, which is NCV delta T. And now the final temperature is the hot one minus the cold one. And so this is a positive temperature difference. And so this is greater than 0 and positive. So these two are equal magnitude, but opposite sign. So if we do one of those, then we can flip the sign and we've got the other one. So we do the adiabatic expansion, cold minus hot, CV, number of moles. We get a certain number of joules that have been doing work on that adiabatic expansion. The compression is just resetting that temperature from cold back to hot. Nothing else has changed in the system in terms of the temperatures. And so we just flip the sign and you've got the other one. These two are different, though. The isothermal expansion is happening at a high temperature. The isothermal compression is happening at the cold temperature. So because these temperatures are different, the VA and VB, VC and VD, those are all different volumes. The isothermal legs have to be calculated independently. They're not like equal and opposite signs. And then once we end up at the end, we can calculate the net work for the cycle and divide by the heat in. So the heat in right here is this one up here. What we took off of the hot. So Q in is equal to minus WAB. Okay, so this is just an outline of the equations. Let's do a problem from beginning to end. We'll start with the various parameters. This is just text essentially in your notes. Heat's absorbed from the reservoir. There's a positive entropy change. Then we have the expansion. We go from hot to cold. Entropy change is 0. So this adiabatic expansion can also be called an isentrope. So we got another one. Although because we have two vowels there, we drop the O. So it's instead of isoentropic, it's just an isentropic. We'll see that in the Brayton cycle, the jet engine cycle, where they label it with an isentrope instead of calling it adiabatic. Okay. And so here's this idea, this perfect Carnot engine. We can calculate that efficiency. This efficiency right here is for all engines, or all heat engines. And we did that with the Stirling cycle. We calculated how much work we had, we calculated how much heat we put in, and we were able to calculate it was 16% efficient. But this one right here, this is for Carnot cycles. So So it can be, you know, you can divide this denominator in two, and so you can have the T hot over T hot is 1. So this is just a simpler way to do it. And notice that you can't get to an efficiency of 1 without T cold being 0 Kelvin. So this is, you know, the spreading these temperatures apart and making cold really cold and making hot really hot, splitting those temperatures, that's how much you subtract from 1. If you get hot really hot, you're subtracting a tiny amount from 1. And so this is, when I say for all heat engines, that would be the efficiency of this irreversible engine here. The reversible engine here is given. So this, you could say that, I'll get rid of this REV. So for a Carnot cycle, they're equal, but if we're doing any kind of engine, we can always calculate the efficiency for an irreducible or irreversible engine using W cycle over QAB. Now, what if I don't have a Carnot engine? I can break up any cycle into a bunch of different little Carnot cycle parts. And so this is how a real engineer would do this, a mechanical engineer looking at a real engine with its real volumes and cylinders and all of that, would have a computer simulate the area in this, say this strangely circular or oblong cycle diagram into tiny little Carnot cycles. Because the work that comes out of the machine is proportional to the area inside that cycle. Okay, so if you could calculate that area more efficiently or more accurately with these little Carnot cycles, it's kind of like what we do with the molecular wave functions and so on. We use Gaussians. Now those wave functions aren't really Gaussian, but we can model them with a bunch of Gaussians. We'd do the same thing here. This cycle, say in a diesel engine or a gasoline engine, is not a Carnot cycle, but we could take that diagram and break it into little bits and use Carnot cycle math for each of those little bits. Okay. So let's do a real problem. So we can calculate we can use this compression ratio calculator. We'll just use a monatomic gas for a working fluid. And then let's practice converting temperatures. So what is 210 Fahrenheit in Kelvin? So let's do Fahrenheit to Celsius first. Yep. So we have TF minus 32, right? So that's how much it is above freezing, okay? And then what's the conversion ratio of Fahrenheit to Celsius? Do y'all remember that?
I don't know.
5/9, yeah. If you forget, okay, here's the thing. So let's look at water. So it's boils at 100 C, and it freezes at 0 C. And what is that in terms of Fahrenheit? That's 212 Fahrenheit and 32 degrees Fahrenheit. So this difference right here is 180, and this difference here is 100. So the ratio is 180 to 100, which simplifies to 9/5. Okay. So you can always rederive that if you just remember water, because the difference in boiling water is the same amount of heat, no matter. So those have to be the same temperature. Boiling water has to be the same temperature, no matter what number you put on it and what unit. So anyway, that gives us a 5 degrees C for every 9 degrees Fahrenheit. So our Fahrenheit cancels and we get degrees C. And then we add 273 to that. Break out my calculator. It's a good review. What do we got? 210. 2. If you catch a mistake, remember I've got stickers. Okay. Um, 0.04, but we don't have to go that detailed, but still, that's what I get. You can check my math. If we're going to do a monatomic gas, where does that come into play? What do we use that information for? CV. Very good. CV is equal to, for monatomic gas. Yeah, translation only. So we have 3/2 R, and then CP is another 2/2, so 5/2 R, and therefore gamma is equal to CP over CV, which is going to be 5/3. Okay, so that'll help us with our adiabatic relationships. And then we want to know how much work is produced, how much heat is consumed, and what's the efficiency. We'll compute it both ways. We'll do the net work over the heat in, and we'll use the temperatures. What did y'all get for the 1200? Okay, that's good enough. 922. Okay, so now let's get our engine information. But remember, down here is the displacement. This is delta V. And here's our compression ratio, RC. So we can pull those off of this chart. 2.491 liters. We want to work in liters. And so here's our information. We've got the equation for VA, is that delta V over RC minus 1. So we had from the previous chart, 2.49 liters, 9.03 was the compression ratio. We calculated our T hot in Fahrenheit, but it was 922 Kelvin. And what was the cold? I forgot. 372. Okay. And that's the same temperature at point D. And then the point B also is 922. Now for the PSI, I looked it up. The gasoline engines, it says the max pressure that you get out of the typical engines is 2100 PSI. So we want to convert that to atmospheres, okay? So that we can use the gas constant that we've memorized. So do y'all know how many PSI are in an atmosphere? Good, lucky for you, on the little periodic table that I give out in the exams that's typically attached to the exam, it has it on there. Okay, and it's 14.7 psi. 14.7. Okay, so that's 143 atmospheres. So let me check that again. Yeah, 143. And you can see it up here. It's very close to 143. Okay, now we've got, let's go ahead and calculate our volume A. So 249, I'm sorry, 2.49. 49 liters divided by 8.03. So 0.31. Let's calculate how many moles of gas we have in there because we know the temperature, we know the volume, and we know the max pressure. So let's use the gas law to calculate our number of moles. So let's just do this over here. We've got 143 atmospheres in 0.31 liters. Gas constant. See which one I'm using, the 0.08206 and 922 Kelvin. Three, 3, 1. So 0.586 moles. So okay. So now we have that same amount all the way down. We could calculate VC. If we're looking at all of this, we've got an equation for VC. So that's 2.49 plus 0.31 liters. $2.8. Good job. We could check our work on here. So we've got VA and VC. This is 0.31. I try to give you, well, I do. I give you an accurate plot on the exam. Okay, so you can check your work. And that way, you could estimate that, but I don't want to see an estimate. I've seen people that do it, they'll get partial credit, but I want you to be able to check your work, if you're looking at this plot. You want to be able to do that. Now, we could calculate this pressure. So 0.586 number of moles times the gas constant, 206, times the cold temperature, 372, and divide by 2.8. 6. This is pressure at C. I'm coming up with 6.39 atmospheres. Okay. Again, check my work if you catch an error. Okay, so now look at these two rows. You see why we needed the adiabatic relationships. Because for these two rows, we have two unknowns. And there's no other way to get this volume of B or the volume of D without using this gamma relationship. Okay. And so that's what we're going to have to do. So we're going to take the VC, which is 2.8 liters, T cold, 372 Kelvin, over 922 Kelvin. Raised to the 1 over, and what do we say, 5/3? Previous page. What was it? 5/3, okay. 1 over 5/3 minus 1. So 5/3 minus 3/3 is 2/3. We're going to flip that upside down. So three halves. Did I do that right? 3/2. Yeah. So we got 1.5 to the 1.5 power. So this whole thing is to the 1.5. This whole thing is equal to 1.5. Does that make sense? Okay, so then we're going to do that. 372, 922 divide. And then I've got a y to the x key. So I'm going to put in 1.5 and hit that key. And I get 0.256 times 2.8. 0.781. 718 liters. This is 0.5, this is 1, this is 0.7. That makes sense with the plot, okay? Let me calculate it if I got my temperatures wrong. Okay, since we're here, let's just look at ways we could screw up. So 922 divided by 372 to the 1.5 power. So I think I'm using the equation, right? And then 2.8 times. I get 10.925 for the volume. 10. Yeah, and look at VC. VC is 2.8. It's definitely under 3. And this is calculating 10 liters. So VB can't be 10. So I got something wrong. Okay. Yes. Yeah, it's going in a clockwise motion. So VB has to be between A and C. So if you get that, you're like, wait a minute, that doesn't make any sense. Okay. So then go back and check your work. Can I get somebody to calculate the pressure for this one with the volume, temperature, and a number of moles? So if someone calculate P. You got, see, oh, and the pressure? Okay, good. I thought you were saying the volume was 61. No, 61.7 atmospheres. And so that looks right. See, here's 60. So that's a little bit above 60. Now let's do the volume at point D. So this is connected to volume A. So we use the 0.31 liters. The temperature A, so 922 is on top this time over 372. And it's raised to the 1.5 power. Okay, so that doesn't change. 922, 372, divide 1.5, y to the x, and 0.31 times 1.21. And that looks about right too. And then someone do the pressure for me. There, we've done the state variables table. Not too bad. Some Kelvin, some Fahrenheit to Kelvin calculations. We did some ideal gas law at least 3 times. And then we have these adiabatic relationships. So what I'm looking for on the exam for sure is I want to see you do the adiabatic relationship calculation accurately. So I may give you a state variables table that's missing some of these numbers, and one of them will be either the volume at D or the volume at B, because I want to see you use the adiabatic relationship. And it won't be a monatomic gas, it might be a linear gas, or it might be a nonlinear gas. So that the gamma is changed, gamma is different. So if you just memorize this and you get a different gas, that's not going to work. Okay. Yes, and because we don't have enough information to solve it with the ideal gas law. Yeah, so if we had the pressure at that point, then we could just use the ideal gas law. So if we had this and that, then we could just use the ideal gas law. But it's because we don't have enough information and we have to find another way to solve that problem. And because it's on an adiabat, we can solve it using these adiabatic relationships. And that's the thing that I think people miss. They're like, I don't understand why I have to have this relationship. Well, try to do it without it. You won't be able to. Okay. So that we're not done with the problem though. This is just the state variables. So these are the A, B, C, and D points. Now we can do delta T's to calculate the work for this adiabatic relationship, or we can use the work equation for isothermal expansion. So let's go ahead with those data points and start doing these calculations. So I'll ask you to call out the numbers. So the number of moles, 586, yeah. 586. I'm going to use my units to show you good practice. Now, which R do we use for this one? We're calculating work. I would prefer to get my work in joules. Okay, so use the 8.314. Yeah, 8.3145 if you want to keep all of those joules per mole Kelvin. Okay, so you see the moles cancel. That's beautiful. Now, which temperature do we use? Well, it says T hot here because this is the isothermal expansion AB. We're running along that hot isotherm. So we're putting heat into the system to keep it on that isotherm. So that's, was it 922? And then the natural log of the volume at point B, which was 0.718 liters over 0.31 liters. Okay. And we can't forget this minus sign way out front. Okay. So 0.718, 0.31 divide, natural log. I get 0.84 for the natural log. 22, 314, and 5. Negative, let's go ahead and do kilojoules, negative 3.73 kilojoules. I got 37, negative 37, 34 joules. Okay. Okay. Did y'all get that? Are you following along? All right, now let's do so the heat, this is the work AB, so QAB is equal to that same number with a different sign, plus 3.73 kilojoules. All right, so now let's do the work at going down the adiabat. So we have 0.586 moles. The CV, so we only had some monatomic gas. We only had 3/2 R. Was it 372? I have a memory of a gnat. Okay. Yeah. Negative 4,020. Or negative 4.02 kilojoules. And QBC, trick question. It's listed up there. It's adiabatic, so Q is 0 on all the adiabats. Okay, so now we know that that's the adiabatic expansion, the adiabatic compression. All we do for that one is just swap hot and cold. It's the same difference, but same magnitude, different sign. And so this one is going to be equal to plus 4.02 kilojoules. So even though it looks like we have 4 problems to do, we really only have 3. And then let's do this one here. Minus, if we're running out of time here, so minus 0.586 moles, 8.3145 joules per mole Kelvin. Now we have the T cold, so 373 or 372 Kelvin. And then we have the volume D. So someone get that for me. (1.21), and volume of C was the big one. Okay, liters. And so that one's going to be less than 1, so that log is going to be negative. So we have 1.21 to 2.8 divide natural log. I get minus 0.839, then 372 times 8.3145 times 0.586 times, and I change the sign. So plus 1520. Or 1.52 kilojoules. So that's the work done on that isothermal compression. So we got 3,000 or 3.7 kilojoules out when we did the expansion on the isotherm, pulling in heat. But then when we compressed it, it only took 1.5. So that was great. We're compressing a colder gas. That's easy. That's also what makes an engine go. If you think about it, the gas pushes on the piston, but then when the engine comes around, the piston has to compress the gas again. That gas has to be colder, otherwise the engine will stop. And a lot of engines, like 2 pistons, just think of 2. One's expanding while the other's compressing. So we're using up some of the work of the engine and the power stroke to compress the next gas cycle. And if it wasn't at a colder temperature, you'd have, the forces would balance and it wouldn't turn over. Anybody ever try to start a lawnmower, a pull start lawnmower? When it's cold, what happens? Right? So the expansion, you're not getting enough work on the power stroke to shove that thing around and compress the next gas because it's not warmed up. But once it's warmed up, you get so much more power out of the power stroke that it's easy to compress the cold gas when it comes in. But until we get a good separation between the hot and cold reservoirs, in other words, we warm our engine up, it can't do the compression piece because the temperatures aren't far enough apart. You get those temperatures far enough apart, we've pulled enough heat out of the hot reservoir to get a power stroke that is enough to carry enough energy into the compression stroke, and then the engine can start again this cycle. Now, I'm always doing my cycles clockwise for me, but they're backwards for you, so I'm sorry. We need to go like this. All right, so here's our answer key. How'd we do? Okay. Now, we didn't do our temperatures. So we have our heat in. So that was this guy, 3.73 joules or kilojoules. And then the net amount of work. Okay, so we had this 4.02 here cancels with this one. So we don't really have to take into account the adiabatic expansion and compression because those cancel. When we're adding them up, see, it's all of these works added together. And so what we really need to see is just the difference between 3.7 and 1.5. So we have, whoa. minus 3.7 plus 1.5, and we're going to take the absolute value. So what's the difference between those two? 2.21. Okay, so we have 2.21, 2.21, enter, and then we're dividing by 3.73. So we get about 59%. So this is 0.59. Let's look at the temperatures. We had efficiency for the reversible engine was 1 minus T cold 372 over 922. 372, enter, 922, divide, and then we could do 1 minus. So equal to 0.59. So whether we calculate it with the work or the temperatures, we get the same efficiency because this is a Carnot cycle. If we did this with the Stirling cycle, the Stirling cycle was like 16% efficient using the work numbers and the heat number. But if we looked at those temperatures, it should have been like 34 or 35% efficient. So our engine isn't running as efficiently as it could because it's not mimicking a Carnot cycle. The temperatures that we had in the little oil lamp and room temperature, if those are hot and cold temperatures, we could get 34% efficient out of that Stirling cycle. But the Stirling cycle engine isn't a Carnot cycle. So it's less efficient mechanically, and it could only get 16, 17% out of that just because it's the way it's mechanically designed.
The last W, B, or DA.
This one here, WDA, that's that going back up. Oh yeah, this one here, this should be A, yeah. Thank you, good catch. I'll get you a sticker. Okay. Okay, so now this right here is all obviously in a spreadsheet. And so I would like for you guys to build this for that extra, points on the exam, for the bonus on the exam. So all the equations we just did, it's kind of a pain in the butt to do this. And then I say, okay, now do it for 800 Kelvin. You got to do every one of those darn things again. And that's why I like Excel, right? You build the equations once, and then you go up and change delta V, or change the compression ratio, or change the pressure max, or change the temperature, or change the gas from monatomic to linear to nonlinear. Okay. And so this is going to teach you a lot about the Carnot cycle because you're putting in all the equations and building a Carnot cycle spreadsheet that you can play with. And so you've got a week, to do that. So this will be, I'll put up a link for next week's, for this thing as part of points on your exam. Once again, it's bonus, but it'll really teach you and help you prep for the exam. You can take, you don't have to do it, but if you do it, it'll be up to, I'll probably do 20 points again because it was really good last time.